Let's begin to the next simulation. In this simulation, we are going to simulate shunt active power filter based on DQ domain transformation. That is by using DQ0 transformation for the active power filter with instantaneous power theory developed by Akagi. So let us develop first the power circuit. For a power circuit, we need three-phase source. Okay, to just take the three-phase source first. This three-phase source is set to 400 volt 50 hertz. Resistance is equal to 0.9 ohm and inductance is equal to 0. So let's begin with this. So here I'm setting this three-phase source to 400 volt, star ground connection, 400 volt. Frequency will set it to 50 hertz. The resistance I will specify it as a 0.9 ohm, inductance 0 on the base of 400 volt supply. So this we have done. Now we take a three-phase VI measurement block. So let's take three-phase VI measurement block. Double click on this three-phase VI measurement. We want to measure the phase to ground voltage. Use as a label. You rename this with the VS, and the current measurement is with dias because this is source current. Okay, now you can observe here A, B, C quantity. Okay, so let's connect this together. Now we have to design a non-linear load. To design the non-linear load, take a diode bridge rectifier, or you take universal bridge. Okay, you take this universal bridge. In this universal bridge, you choose the diode rectifier and 3-arm bridge. Okay, so this is a diode rectifier. Okay, now we have to connect the load on the output side. Let us connect the load on the output side. Take series RLC branch. In this RLC branch, set the RL value with the resistance of 10 ohm and inductance is of 1 millihenry. The inductor is already 1 millihenry. Okay, rotate this, connect this to, okay, here. Now we want one more measurement block, so I will copy this measurement block. In this I will rename this with the load side voltage, load side current. Okay, 1 minute, I got one mistake here. It must be I underscore S label. So here I underscore L and V underscore L. So let us connect this together. Let us add the measurement to just see the output. Take the block of from. Okay, in this from block, let this is equal to Vs, then drag the same, it is Is. Okay, this is VL, this is IL. Okay, actually VL is not needed here, then also I am measuring. Okay, take the scope. First we will see the uncompensated output and then we will see the others. Double click on the scope, open its settings. First time scope take the time to open. Okay, let's set number of input ports as a 4. Choose this layout. Okay, now increase the scope size. Okay, so this we have added the measurement. Let's create the area for this. Okay, then I need a power GUI block. So let's take power GUI block. Okay, in this power GUI block, make it a discrete and step size 50 e raised to 6. We'll keep 50 e raised to minus 6 as it is. Now let's run this simulation to check whether it is performing as per expectation or not. First time it will take time to compile. Okay, I have not changed the simulation time. Once it is compiled, I will change the simulation time. Okay, it started running, completed 100%. So let's change to 0.25 time and run it. Okay, the simulation is completed. Okay, let's check. So you can observe here in the load current and source current have harmonics. So if you observe here, the source current and load current is not a sinusoidal value, it is having the harmonics. So how to reduce this harmonics, that we will see in the next, that is we will design the active power filter for this. First we'll check the THD, total harmonic distortion. Okay, you go into the app, then go into the FFT. Okay, let FFTs to appear. Okay, if you see here, this list is empty. uh, how to come with this list? Go in the modeling, then in modeling go in the model setting. In this model setting we have to configure the parameter to get the FFT analysis. So go in the data import export and untick the single simulation output. Okay, I have untick this. Apply. Again come to this section. Here go into the setting, go into the data logging. Okay, you can give with the structure with time. Okay, scope data. Now once again I will go in the simulation and run it. Okay, so the waveform is appeared over here. Now go to again FFT analysis. Now you can see the waveform is appeared automatically, but this is the what first one output voltage, this is the output current. We will start measuring in harmonics from 0.15 for the cycle of 4 cycles. Let's take only a 50 window into the calculation. Our base frequency is a 50 hertz, and click on the compute FFT. So you can observe the THD is 27.42%. The same THD you will observe at the load current side also. Load current side THD is also 24.42%. Now how to reduce these harmonics? We have to design the shunt active power filter to reduce these harmonics below some level. So to design that we need a voltage source converter. How to design the shunt active filter? We will see. Take a again universal bridge. Okay, universal bridge. In this universal bridge, let me shift this measurement block downside. In this universal bridge, rotate it, change this as the, you can choose MOSFET IGBT. I will choose the IGBT best. Okay, right click on this universal bridge, go to the mask, sorry, format. In a format, you click on flip block as left to right, then your ABC will come here and gate is here, plus minus terminal is here. Now we want a DC supply of 700 volt here, so we will take a DC source. Okay, DC voltage source. I think I have chosen the wrong DC source. Let's check. It is not from the electrical library. Let it is to be up here. Okay, I have chosen this you cannot connect this. So DC voltage source you took is from the specialized power system. So this DC source, rotate it, connect plus to plus, minus to minus, set this DC voltage to the 700 volt. Now you connect this A, B, C with the respective phase, but we want the inductor in between. So let us have the inductor three phase series branch, three phase series RLC branch. Double click on this, choose the only inductance, and inductance value must be 2 millihenry. Then rotate it. Okay, connect. Okay, now before connecting this to here we need a measurement block again. So this I will copy, control rotate, capital ABC on bottom side. You connect A phase to A phase, B phase to B phase, C phase to C phase. So here we need this as the compensating voltage VC and compensating current IC. Okay, now we have to design the gate pulse. You take the block of from, we have to design the controller. So controller will give the provide the gate signal. So how this gate signal we can apply, that we will see in the next lecture. So we before get how to design the controller using instantaneous PQ theory of the Akagi, that we will study in the next session. Hope you will like this video. If you like this video, kindly subscribe my channel. Thank you.